Welcome to the pre-class video assignment for section 3.2. So in this section, we're going to actually look at solving second order DEs by power series. In particular, the type of power series we can deal with here looks like this, or even, so this would be the type of DE we can deal with here looks like this. P, where we have, again, coefficients P0, P1, and P2. P0, P1, and P2 can be up to being polynomials, and we will also assume that any factors they might have had in common have been cancelled out. So again, you can divide through a common factor through this entire DE. Again, we can also deal with initial value problems if necessary. So in general, it is often not possible to solve this type of DE to find elementary function solutions, but here we can see how to find power series solutions. Also, again, we've also found it difficult to solve where we have non-constant coefficients here, so we can also solve DEs using power series where we have polynomial coefficients P0, P1, P2, and so on. First, let's talk about existence. We already have a theory for the existence of a general solution for one of these. So in standard form, where we have second derivative plus P dy dx plus qy equals 0. In this situation, basically we're considering p of x in standard form. This would be where we've taken our p0 and divided it through the DE. So p, the function little p here, is just p1 over p0. Q is p2 over p0. So we looked at this standard form in section 2.1, and we found that, or we just stated that we have a unique solution to an initial value problem in the largest interval that contains x0, but not any discontinuities of px and qx. So this means if we can look at the place where we are, if we look at the place where we have our initial condition defined at x0, we will have an interval of definition that extends at least from x0 in a symmetrical fashion out to the nearest place where we have a discontinuity. So notice in our case then, P0 is a polynomial, and so the only place we will have a discontinuity for P or Q would be where P0 has zeros. So that is what is significant here. All right. So a little terminology here. A differential equation has a so-called ordinary point at x0 if x0 is not a zero of p0. So again, if we're looking at this leading polynomial that we have there, as long as x0 is not a zero of that polynomial, this is an ordinary point. So an ordinary point is in some sense a nice point for a DE. It is a place where the P and the Q are continuous. If a point is not ordinary, then we call it a singular point. So a singular point would be a place where P sub 0 does have a 0. So zeros of that leading polynomial P0 are singular. And again, this is a less nice feature. This is not a nice feature of a differential equation. All right, so we can state then the existence of power series solutions in terms of ordinary points. The existence of a power series solution. If x0 is an ordinary point of one of these DEs, so again, we're talking about one of these DEs, if x0 is an ordinary point, then every solution to the DE can be represented in the form of a power series centered at x0. So basically, we do have a power series solution centered at x0 as long as x0 is ordinary. So that's a good thing. We can't, this is basically stating in these types of DEs with polynomial coefficients, we do have power series solutions at ordinary points. Follow-up is that the follow-up idea here from this theorem is that the radius of convergence for such a power series solution is at least r, where r is the distance from x0, the ordinary point, to the closest singular point in the complex plane. So again, we also have a way of looking at what the radius of convergence would be. Now, that's, again, a theory that works nicely for ordinary points. Singular points can actually, in theory, have power series solutions defined at them, but the method is different. We will not be looking at it in this section, less convenient. But at ordinary points, there is a power series solution. So let's talk a little bit about this radius of convergence. In theory, this is based on the complex plane. So what is that talking about? That is talking about the real number line crossed with the imaginary number line. So if you haven't seen any complex analysis or complex number, a complex number can be plotted in a plane very much like a coordinate plane. So if you have a complex number like a plus bi, we can plot this in the complex plane, plotting it as if it were a comma b in the xy plane. So if you understand that, and that's not too difficult, then all we're saying here is we would need to singular points are zeros of the leading coefficient polynomial p0. So I need to look at the roots of p0, but I also have to look at not only the real roots, but also the complex roots. And if you have real roots and complex roots, so you can have here's our real number line, we could have a complex root plotted in the complex plane, and in which case the distance r, we would have to take into consideration this distance in the complex plane. Now, I'm going to go ahead and assume that not everybody knows about this, so we will not worry about examples like this. We will only have polynomials with real coefficients to avoid this situation. So in the real number line situation, if all our zeros are real numbers, then we can simply look at this on a number line. If the center is at 0, as depicted here, and then we can simply go look for our closest singular point, and then this would give us our radius of convergence, and then this would determine an interval of convergence. An interval of convergence is always symmetrical about that center point. So again, this is a fairly easy idea. All right, so forgot to do, how about we do a couple of little questions about ordinary and singular points. And then there's a second one. All right, so let's try and answer a question here. A couple of questions here. For the following DEs, determine any singular points and determine the, that's a typo, determine the minimum radius of convergence for the power series centered about the given ordinary point. And again, the idea here is to not solve it and find a power series and then try and determine a radius of convergence. We can do this from the part of the second part of our theorem here. So for this particular example, here is our differential equation, second order. It has got polynomial coefficients only. So all we really are worried about then are singular points, which are the zeros of this polynomial coefficient here. So if we look at the zeros of this, that's fairly easily solved. The zeros will be x equals plus or minus 1 over root 2. These will be the singular points of this DE. And then fairly simply, if we are centered about 0, which is actually going to be the case 99% of the time, we look at our center point, we consider where we have our singular points, and then the radius of convergence is simply that distance, at a minimum, that distance. And again, therefore, the interval is at a minimum from -1/√2 to 1/√2. This would be our minimum R. The actual R could be bigger than this, but it's certainly at least this much. So that's a pretty easy one. Slightly more complicated. Here is another P0 polynomial coefficient. And again, the singular points are where this polynomial has zeros. So we set this polynomial expression equal to 0 and solve. So this is what it looks like factored. Again, this is probably a bit of work to actually factor. Let me expedite here. Your choices here are you could probably graph this on a calculator and look for x-intercepts, or you can use the rational zeros theorem to factor this guy. But this is what it factors into: x minus 1, x plus 2, 2x minus 5. So it has zeros at x equals +1, x equals -2, and x equals 5/2. These would be the singular points for the DE. So to come up with a minimum radius of convergence, I think about where my center is. We're going to center at x equals 2 this time. And then I just want to consider where is 2 in relation to these singular points of -2, +1, +2.5. And again, I think fairly obviously, the closest singular point to 2 is at 5/2, 2.5. So the distance between them is 1/2. This would be our minimum radius of convergence. Again, so this is a little background theory here about the existence of power series solutions. All right, so give a question like that a go. All right, so next up, we're going to look again a little bit more at the method for solving, finding power series solutions of second order DEs like this. We've done a couple of examples in the last section for first order. For second order, this should actually be, this is 3.1. So we saw, this is basically the same method, but it's just for second order. Again, the method is we assume we have a general generic power series as a solution. For our purposes, we can go ahead. We will basically always have the center at x equals 0. So I really don't need to remember it this way. I just want to remember it like this. This is going to be my generic solution here. It is going to look like this. So to substitute this solution into our DE, I need its first and second derivatives. So remind yourself about those. Again, those should be fairly easy. Again, I'm really just wondering, this should be something we need to commit to memory. Every single one of these problems will start here. Start with just defining a particular solution, a power series solution as a generic power series, and then finding its first and second derivative, and then substituting these in. At that point, we need to combine our power series into a single power series, because then we can use this identity property we learned about last time in order to solve. So we will see examples of this, but our first goal is to add these power series together. So let's take a look at that real quick. Adding power series together. How do we do this? So we did start to look at this in 3.1, but this is kind of critical to getting these power series solutions. So let's remind ourselves, and I'll have you do a couple of examples here. But for example, if we were to try and sum these two power series write them into a single sum, how would we do that? So the process would be, first of all, I need to bring everything inside the sum. So I need to bring the 3 inside. I need to bring the x inside. It's sum. The 3 inside is really just distribution. So I can literally just bring it inside. The x bringing it inside is also distribution, but we basically end up with x times x to the n, which would be x to the n plus 1. So this would be the first step, making sure we just have these two sums. And then the goal is, in order to combine these two power series into a single sum, I need two things to happen. I need the powers to be the same so that I'm combining like terms effectively. And then I also need the indexes to start in the same place. If I can fix those two things, I can simply write them with a single summation. So we need to make those two things happen. Now we have to make them happen in the proper order. So you always fix the powers first. So to fix the powers first, you simply substitute in a common power. So what I would usually do is basically turn x to the n minus 2 into x to the k. That is, let k be equal to n minus 2. If k equals n minus 2, then n equals k plus 2. And substituting everything in. If n equals k plus 2, you've got k plus 2 equals 2 or k equals 0. And then over here, we're going to substitute away the n. N is a k plus 2 and a c sub k plus 2, and then x to the k. That was what we were after. For the other sum, I have to do the same thing, but it requires the substitution, let k be equal to n plus 1. If k is equal to n plus 1, n is equal to k minus 1. If you put k minus 1 in for n here in the index, you would end up with k equals plus 1. And then if you substitute n by k minus 1, we get k minus 1 x to the k. So this is what we have. We have now rewritten these so that they have the same power. That's our first crucial step. Unfortunately, even though these have the same power, I can't combine them yet because they don't start at the same place. One of them starts at k equals 0, one of them starts at k equals 1. So our next goal is to make both of these indexes start in the same place. And we do this by always making it start at the later place. So look at it this way. Basically, this sum over here has one extra term at the beginning. It has a k equals 0 term at the beginning. This one does not. So the simple idea here is I am just going to peel off the term for k equals 0 and write it out separately. And then I will have a sum that starts at k equals 1. So notice if you plug in k equals 0 into this first part, we would get a 0 here. So 3 times 2 is 6, c sub 2. And that would be x to the 0 is 1. So I just have 6c2. So if I peel off that 6c2 and write it as its own term, then this first sum now starts at k equals 1, just like this one did. And now we're in business. I have the same power in both. I have the same index to start with for both. So you can simply write these with the same into a single sum. So I still have the 6c plus 2 at the beginning, but now I have the sum, k equals 1 to infinity. And then I can really just write these out. So I wrote them into a single sum, but I also factored out the x sub k so that we now have this coefficient, effectively, as messy as it might look. We have this coefficient x to the k. So this is an important skill that is crucial to doing these problems. So there's a couple of examples to practice on. And then a second one to try that out on. All right. So lastly, before we leave it here, I just want to go through the beginning of the next problem. We will still complete this problem and talk about this problem in class together, but just to motivate where these things get started from. So here is, believe it or not, this one's a fairly simple one. Again, these tend to be hard. Even the easy ones are kind of hard. But let's just see the process. We are attempting to solve this second order DE. Again, the process is we simply assume that this is our generic power series solution. We need first and second derivatives, so we can find first and second derivatives. And again, every problem starts out with this same start. These are always the same things we need to start with. So then we can plug them in. I put my y double prime in. I have a 2 times my y prime equals 0. So this is now my DE with those substituted in. And our goal then is to write this left-hand side as a single sum, combine them into a single sum. So the trick is, as usual, the 2 needs to get moved in on the inside. So I move the 2 on the inside. I then need to fix my powers. So for this first sum, I let k equals n minus 2, and n therefore is k plus 2. And making those substitutions, I got this guy here. So pause and double and think your way through that yourselves, just to make sure that you're clear on that. And then I do a similar trick over here. I'm going to let k be equal to the n minus 1. Using that substitution, I came up with this sum. So again, just take a minute and satisfy yourselves how that works. Then let's see, we got lucky on this one, that by making these fixes, we actually do have indexes that start in the same place. So I'm all ready to go here. I don't need to peel anything off. I can just go ahead and write them as a single sum. So I write this in here plus this in here, but again, in the same step, I am factoring out the x to the k, and then this is my coefficient, my general coefficient. So that is a skill in itself, getting from here to here. This is basically, again, a good skill. And this is your last example on My Open Math to try out. So give that a go. All right, so just a little look ahead. The idea then is that now that we are here, we have a single power series equals 0. So the identity property says the only way that this is an identity is if the coefficients are 0. So that basically allows us to take this whole coefficient and set it equal to 0. This is the only way that is possible. By doing that, we now have a formula, if you like, that relates our coefficients together. Here I have a formula for c sub k plus 1 and c sub k plus 2, and we can work from this, plugging in different k values. We can attempt to figure out what the relationship is for these, or what the values are for these coefficients, c sub k plus 1, c sub k plus 2. So all these we can plug in k equals 0, k equals 1, k equals 2, and try to figure out what these coefficients are. This is something called a recurrence relation, but we will revisit this question in class together, just to have you give a little head start. Otherwise, we're going to leave it there for today, and I will see you in class to finish this up.